Welcome back to pentagramprime. Today's lesson will be a compare and contrast between using Weierstrass substitution and residue theorem to solve a trigonometric integral. First, apologies. I had a little emergency last night. My ATM card got stolen, so I was up late dealing with police, a fraud investigator, and a few other people stuff. So all of my time to do the editing on this pretty much went out the window. The original plan was to I was going to shoot 2 episodes, well, basically 2 lessons, and paste them together. And I am still going to do the lesson residue theorem, but what's going to happen is that's going to be shot using paper and pencil at the end. Also, this I don't have any time for editing, so I'm going to read through the script and scroll through the formulas, and then from there we'll hopefully that gets the point across. So I'm probably going to go back to using pencil and paper starting with next week's lesson because it's just quicker. For a weekly lesson, it's not serving me to use an equation editor, I'm afraid. So we're going to jump right in with an overview of Firestraw substitution. So this is the integral we're solving. 1 over 13 plus 5 cosine theta integrated from 0 to 2 pi. I think, Firestraw substitution is also referred to as T substitution, and if you're even dreaming of using this beast, please keep the domain of the tangent function in mind, because unfortunately you cannot use odd multiples of pi in this function. Pi, 3 pi, and so on are all basically dirty words for the purposes of working on one of these problems. In Kerbal Space Program, we refer to it as check your staging. I also think Harold Ramis should be awarded a posthumous honorary doctorate in physics, insofar as it's in my power to say so. So right from the get-go, we need to take these bounds of integration from 0 to 2 pi and split them into 2 parts. We'll come back to this expression later, but I wanted to make sure that was pardon me, stated at the outset. So, through the miracle of calculus, algebra, and trigonometry, we get the following expressions for d theta, cosine theta, and sine theta. And in case it wasn't obvious, we won't be needing the expression for sine theta this time around. But before I forget, if you're like me and you've tried to commit the sine and cosine formulas to memory, you might get tripped up on which t expression belongs to the sine and which one belongs to the cosine. You can't have yourself thinking that sine theta is equal to the 1 minus t squared over 1 plus t squared, when in fact it equals 2t over 1 plus t squared. So really, just to keep these straight in your head, all you have to do is keep in mind that the sine function is an odd function, like 2t over 1 plus t squared, and the cosine function is an even function, like 1 minus t squared over 1 plus t squared. And also, the conversion between d theta and dt is basically like the formula for the sine function, but you swap out the t with the dt. So inserting forward d theta and cosine of theta into the indefinite integral, we get, and boy, this is taking a long time, we get an integral in terms of t. Multiplying the top and bottom by 1 plus t squared, and pulling out the factor of 2, we get a quadratic in the denominator, and simplifying, we get 8t squared plus 18. Dividing top and bottom by 2, we get 4t squared plus 9 in the denominator. And factoring out the 4 while converting the term to the right of the denominator into a square, we have a rather familiar looking integral, or so I hope. I mean, do I really need to show you how to solve this? I mean, Residue Theorem was in the title, so come on. And we have I equal to the multiple of the arctangent function of t divided by 3/2. And it just hit me that I'm mortal, I have sinned, and the variable I, strictly speaking, is not equal to this function because it was originally set up as the definite integral from 0 to 2 pi. Anyway, yeah, there you go. You live and learn. And I'm out of time on this lesson. I wrote this saying I was out of time yesterday before the other thing I just talked about. So hopefully it's enough that I'm available in the comments to answer any questions you guys have. Yeah. This was funny when I originally animated it. I did want to work from home. Well, tried to, okay. Yeah, I'm going to stop pretending to talk to myself. No, I didn't do that. Okay, yeah, nothing to see here. Yeah, it's okay. She's fine. Well, we'll see if I can get you some more subscribers. So, not at this rate. Anyhow, where was I? Arctangent function, yes. So, we're going to factor out that 2. And get a 1/6 on the left, and here's our antiderivative expressed in t space. Now, I could substitute in for t equal to tangent of theta over 2, but I'm going to hold off because the real question is, what do we do when this becomes this? It's time to look at a graph. So here we have the graph of t equal to tangent of half theta versus theta. Oh, and hold the phone. Had to properly label that graph. So as we approach the asymptote from the right, with the superscript plus indicating the direction of the one-dimensional limit of theta, t approaches negative infinity. As theta approaches pi from the left-hand side, indicated by the superscript minus on pi, we see that t approaches positive infinity. Now, I made a note to self to over-explain what comes next so that future generations will refrain from improperly setting up the bounds of integration the way I did the first time I attacked this problem. Details aside, I naively, or perhaps subconsciously, assumed somehow that since both sides approached pi when integrating in theta space, that both sides would somehow approach the same number in t space, and now I wonder how I managed to finish preschool. While I'm at it, I happened to be watching an episode of Door Monster recently where Kyle C. Sullivan discussed how to be a successful YouTuber. And it caused me to reflect on why I'm up at all hours prepping these equations while learning animation and a number of other things that have nothing to do with math. Kyle makes a solid case that if you're really into, fancy cars and counting paper and, you know, uh, whatever it is people do with lots of money. I saw a guy recently who bought a Harrier jump jet. Um, then you're probably better off just doing something else. And since I'm more focused on integration than on sketch comedy, my projected earnings are far less than his, and he freely admits he doesn't make a lot of money doing it either. So my earnings are at the point of being non-existent. Thanks, Kyle. So I'm not here to, pay the rent. I'm here because I recently spent 2 years doing math in my spare time, and I finally got sick of telling the bartender about it only to hear about how much they hated trigonometry in high school. And since I also suck at marketing, I am still struggling in relative isolation. With that said, please put the word out that I'm looking for viewers who know what 2.718282 is a 7-digit approximation of. So having established how t behaves in the vicinity of theta equal to pi, we can take an informed look at this thing. So this is what's really happening here with the bounds of integration. The two integrals from d theta are the two integrals for d theta are approaching pi from different sides. And that should be obvious to anyone taking Calc 2. But here it's critical because of the implications for the variable t. Actually, if I want to be the calculus equivalent of a grammar Nazi, then I can rigorously set up the limits. To be fair, I learned the term grammar Nazi. I learned the grammar Nazi reference from Hank Green on Crash Course Chemistry. I think he was talking about naming conventions for OrgoChem. And I don't know why I'm bothering with all of these references. I was just informed recently that quality doesn't actually matter on YouTube. And by the way, you really don't need to do this on the bounds of theta because it is implied by convention. The term on the bottom specifies the left side, and the term on top specifies the right side that is approaching a point from the left during integration. But for our purposes here, I want to be specific and spell it all out. There might be a grader out there who could dock you points on a test over whether or not to put these plus and minus signs in the actual bounds of integration, but I wouldn't do such a thing. So now we can fill in the limits for t on the bottom. No mystery here. We're integrating arctangent across boundaries specified by t equal to tan theta over 2. And those of you who know your trigonometry, or those who have simply looked at the previous graph, those of you who know your trigonometry understand that we can just substitute in a couple of zeros. Sorry, I had a typo in the script there. So from here, it might be a bit clearer if I insert limits for the two infinities. Now for the limit on the right-hand side, h is approaching negative infinity. For this example, we can interchange the minus signs so that we have identical limits on the outsides of both expressions. So let's combine these limits and factor out that 1 over 6 in both expressions. And moving the 1 over 6 to the front, we can expand the terms inside of the brackets, and from here we can see that the minus signs on the right hand side cancel, since arctangent is an odd function. And simplifying the middle two terms, we see that they are 0, since arctangent of 0 is 0. So we're now left with two identical arctangent terms. And then let's see, get rid of the zeros, and from here we will combine these two terms and we'll have a 2 times arctangent of 2h over 3. Sorry, this is the part where I stopped writing my script and just we're almost done with this lesson, but I fumbled there for a moment. Alright, so we're going to factor out that 2. This gives us a 1/3 on the outside, and now we just have the limit of arctangent of 2h over 3 as h goes to infinity. Of course, 2/3 h also goes to infinity, and thus the arctangent at the limit of infinity is 2 pi over 2, and multiplying that times 1/3 we get pi over 6. So that concludes the portion of this lesson on Firestraw substitution. I'm going to take off for a moment, and when I come back I'll show the same problem using residue theorem, and I'll be doing that on notebook paper.